Thank you for having me today. My name is Jean-Julien Aucouturier. I go by JJ. I'm a CNRS researcher at the Femto-ST Institute in France. That's in Besançon. That's in the eastern part of France. I'm really happy to be talking to MIR today. Thank you again, Vinu, and the organizers for the kind invitation. I'm especially happy because I was trained originally in the field of music information retrieval, but I've almost entirely left the field now, and I've transitioned to a different field, which is the field of cognitive science and neuroscience. And that was quite the adventure, moving from computer science to biology, essentially. And I've made a lot of mistakes on that interdisciplinary journey, and hopefully I've learned a thing or two as well, and that's what I wanted to talk about today. And I think this workshop, which is interdisciplinary between MIR and cognition, is just a perfect venue for this. So again, thank you very much for having me. I'm really delighted to be here. Like I said, I was trained to research in a couple of labs which were, at the very beginning of the music information retrieval community. I did my master's with Mark Sandler in what was then King's College, just shortly before the team moved to to Queen Mary University of London to create the Center for Digital Music. I then did my PhD with François Pachet in Paris in Sony Computer Science Labs. And that was really just the beginning of the MIR community. I got my master's in 2000, which was the first MIR symposium in Bloomington was about just that day. And after these first 5 years, I've moved to the other side of the country, of the world, to Japan. And that has set a journey to transition to a different type of doing science. I first did cognitive science at the University of Tokyo with Takashi Ikegami and Katsumi Watanabe. And then I went for a researcher position at the Riken Brain Science Institute with Kazuo Okanoya. And that was really my years of training in this new field of neuroscience. Like I said, I made a lot of mistakes. I've compelled my advisors to a lot of patience and a lot of goodwill to train me in this field. And I've moved back to France in 2011. I had a brief stint continuing in the field of music cognition with Emmanuel Bigan at the University of Burgundy in Dijon in France. And I've become a PI in 2012. I've studied IRCAM in Paris for 5 years, and I'm now at the Femto-ST Institute. This brief thing to say that if you look at my records in the MIR conference, you'll see me basically every year for the past 5 years or something. Like I said, I was lucky to be in the starting team of this. Mark, all the time with Michel Fingerhut and Don Bird organized the first two symposium in Plymouth and Bloomington. And yes, I was a regular at the conference, and I really grew to research in the MIR community. So it's a community that's very dear to me. But I've almost completely disappeared from the scene for the past 15 years or so, and that really makes me really grateful for you to have me back here. It kind of feels like coming home in a way, and I'm really happy about that. So basically the topic of this talk is what the heck happened in these 10 years or 15 years, and I've been kept busy, but I'd like to share a few thoughts about what it meant to transition from MIR to neuroscience and cognitive science. So this talk is a journey between two fields, like I said. Let's say on one side, you'll have what we could call music information retrieval, but has also to do with signal processing, with machine learning of sounds, with sound synthesis even. So that's on the one side. The other side of that journey is in the field of biology, and as far as I'm concerned, understanding how the brain handles sound and music and voice. So these would be the fields of psychoacoustics, for instance, cognitive psychology, music cognition, cognitive neuroscience. Now, if you look at these two fields here, what strikes us really is that, in fact, their object of study is really quite similar. In fact, both of these disciplines are studying, modeling, simulating how the brains perceives sound and music, in our case. But they do that with very different methodologies. If you're a computer scientist, if you are trained in MIR and you open a journal, a neuroscience journal, this will blatantly come to you that it's a totally different methodology. There's totally different words. You have to grapple with the neuroanatomy terms, the auditory cortex, so posterior singular temporal gyrus, and all of these things. The paradigms for acquiring data are totally different. The technology, the EEG, the fMRI call for different methods and techniques. Even the data analysis have different norms. So that's fairly obvious to us. On the other side, if you're a biologist and you find yourself in the middle of MIR this year, you'll probably have a pretty hard time as well, grappling with all the technicities and the algorithms and the math and all of that. So these are two fields that basically study the same thing, but with methodologies that are drastically different. And this is me in the middle, basically. I should be moving around here, but it feels like I'm doing the weather forecast here. Basically, for the past 10 years or 15 years, I've been really interested in understanding not so much the different languages, but also the different cultures. I found out that these are two fields which actually have a very different notion of what constitutes a scientific result, what is worthy of publishing in one field or the other, obey to completely different criteria. And it took me a lot of years to understand this. If I have to put this into word, basically what I'm really interested in is to understand how to build scientific proof that's valid in the field of cognitive science and biology in my case, using the tools of music information retrieval. So one first intuition as a MIR researcher that you could have, and that's me at the end of my PhD in 2006, you're looking at the field of psychology and you see all of these people getting participants in the lab. They may bring 20 or 30 participants. They spend a very long time with each of them. You have to get ethical clearance, you have to get consent forms, you have the participants, you need to collect data from them, so you need to build some form of graphical user interface maybe, and then you get the data. You have also different statistical tests, all these ANOVAs and t-tests that we don't really use in the field. And you look at all of this and it looks a little bit cumbersome. I don't really know how to do this and I'm thinking, okay, all of this to basically get data on 10 or 20 songs that you manage to get each of these individual participants to listen to in the course of one experiment. And on the other side, I'm here with my big algorithms and I'm thinking, okay, why can't I just let go of all the participants and say, they are looking at 20 songs, I can look at 20,000 or 20 million for what it's worth. And I have my algorithms, I can run all of these machine learning classifiers on massive amounts of songs. And granted, the algorithms may be only 80% accurate compared to humans, but of all the data that I'm able to gather with the algorithm, surely there's going to be data that's potentially relevant to making cognitive science research. And I'm sure that's an intuition that we have all had at some point, and that was really mine in any case when I ended up with my, at the beginning of my postdoc. And so I was looking at, okay, I have to put a word of caution here. This is incredibly dated as a slide, but backwards in time. This is 2006. MFCCs were all the hype. We had Gaussian mixture models, super vector machines. We use very shallow signal processing architectures. And doing mom and pop machine learning on this basically, but I guess all of the logics would still apply if you replace this for more current models of signal processing and AI. So we have all these tools where we can basically train on a data set of labels that are supposedly of the form of human judgment. So these songs have different genres. This is a rock song, this is not a rock song, and we can train a classifier on this and estimate on new songs. And you can run this on, again, millions of songs. So our intuition was that probably if we look at very many types of labels like this on a lot of songs, we are able to infer data that's relevant to music perception. And that's what we did. We had this big data set of not so much in terms of songs, but in terms of tags, very much like the last.fm data set back in the day, but that was a different, I think this was a source in Sony Music that was private to Sony Music. It's a bit like the Acoustic Brains data set, for some of us who use it. And so basically maybe thousands of different tags going from different genres, different music instruments, different emotions. Is it happy or sad music? Is it music that's suitable for a candlelight dinner? All sorts of tags. And we run all of the algorithms on them and look systematically at the performance of these algorithms on decoding these different labels. And what we found is that in fact there was only a handful of these labels that were decoded very, very well. So the accuracy in the high 80%, 90% basically was only that thing here, only a minority of labels here, and the mass of data was actually barely decoded above chance. And so we looked at this and we thought this probably has some cognitive relevance. I mean, this is probably saying something about all of these labels here that are poorly decoded, and lots of them. They're probably less based on acoustics that we would commonly assume. There may be higher level, there may be more semantic, more symbolic. I didn't know quite, how to call this at the time. But we tried our luck and wrote a very long, complicated, beautiful paper about this, which is saying basically the fact that the physical coupling between the acoustics of the song and the labels is not so high in the vast majority of percepts, you could say, and it questions how much auditory processing there is in the cognitive process of inferring these labels. And we wrote this for the journal Cognitive Science. We're very happy about this. And the paper came back in about 24 hours with a fairly detailed set of review, or a fairly detailed review by the editor, which was very kindly explaining that basically, thank you, but no thank you. And their main argument is actually quite simple. It took me some time to understand at the time, as well as to digest the frustration of not being welcome in that journal. But their main point was that we were basing our argument on machine judgments. We were basing our arguments on a simulation of human behavior made with an algorithm. Their point was, fairly simple. Saying, how can you exclude that this failure to classify music isn't simply a shortcoming of the algorithm? You're saying, our algorithms can't classify all of that stuff. That means this stuff, is not heavily based on acoustics when they're classified by humans. But, you don't base your argument on human judgments, you base it on a simulation of human judgments, so your result may be informative about the algorithms, but they are not informative about the properties of human cognition. And with that final sentence, which is like the nail in the coffin, you should submit this work to an engineering journal instead. Now that sentence I should have really framed and put above my office, because I think I've got this about 10 times in the 10 years that I've tried to submit stuff like this. I still get it now. But this is really interesting as a comment. I should submit this work to an engineering journal. What these reviewers are saying was not that our paper was bad cognitive science, which it probably was, to be honest. What they were saying is that it was an even cognitive science. It's not that there's a bug in the program. It doesn't even compile as an instance, as an example of cognitive science. So this got my head spinning for so much time. And I was talking to psychologists, researchers, neuroscientists, basically with the same question: why don't you like my MFCCs? Basically, what's the problem with this? And one of the things that I understood with the passing of time is that cognitive science, psychology, neuroscience, they're actually not very much interested in the results, but they're interested in the process. What I mean by this is that we in MIR are obsessed with the results, right? We have this 400 songs, 400 rock songs. We classify 392 of these songs correctly. That's 392 over 400 is 96.5% accuracy, which is 2.72% more than the blah, 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 okay? We do this all the time. Psychology isn't concerned about this at all. What they care about is understanding the mechanisms, the process of how you get to the stimulus, to the results. And one example that was given to me by a psychologist friend, and I try to keep this in mind every now and then, they're saying basically psychologists, they see no interest if you show them a calculator, like a hand calculator, a digit calculator, that can compute every single operation super fast, 1,000 times faster than human with no error, and they're not impressed by this. They would be impressed to have a calculator that, say, takes a lot more time to compute 37 times 28 than 3 times 4, as we do, right? So they're less interested in the result than in the process. And again, that seems, a simple argument, but I try to understand that and donning the tools that I had, which are the tools of machine learning and signal processing. I thought, okay, there's maybe something we can do there. So you can use machine learning to compute a lot of results and reason about the results. We understand that's probably no use me bragging about my 20 million songs. The psychologists won't have it, not interested in that. What I can do also is use these machine learning algorithms to reason about the input of the system. So what information is there in the stimulus that's available to the machine to do the task? And reasoning on the information available for the system to do the task is a very psychological question, in fact. And it's also a question which is very difficult to deal with if you're an experimental psychologist. So I'll give you an example here of this. This is fast forward 10 years. This reversed thing is having me for the next, I'm sorry, I'm going to be making a fool of myself with this. So this is a paper we published a bit more recently, which was purely experimental. So this is work with my colleague Clément Canon at IRCAM. And so we're looking at how listeners decode the intentions of musicians when they play. So what we had is that we booked a studio for this. We had two separate booths, two separate recording booths, and we had duets of musicians playing together. We had one in each booth, so they couldn't see each other, they could only hear themselves. So it was just pure musical interaction. And what we asked the musicians was to, one of them in each pair, we gave them a constraint, an instruction, which was to try to convey to the other musicians they're playing with a social attitude. So we had 5 attitudes. There was the attitude of being domineering, of being disdainful, of being conciliatory, caring, insolent. And so these were improvising music, and it was generative improvisation. So they had no score; they were just free improv. And one of them had to play with the other and try to have the other understand that they are being disdainful to them, for instance. And so we ran many. That was a great task. We spent a week in the studio. We had a great corpus. The music is on the internet. You can find it if you Google for it. What was funny with this setup is that we had separate recordings for both tracks, right? We had both separate booths, so we could have one musician and we could have the other musician that they're playing with. And then we had third-party listeners come to the lab, doing exactly what I resented, when I first looked at this. I played the psychologist and invited 20 participants in the lab. And what we did was to see if external listeners were able to decode, basically to recognize what was the attitude being communicated in a given duet. And we did this in 2 conditions. In one condition, they were listening to both tracks. So it was like one musician A playing to musician B. They could listen to the interaction and all of that. And in another condition, we dropped one track. We just basically played musician A, but the participants couldn't hear the response of the other musicians. So they had only one side of the conversation, so to speak. And what we found, in fact, is that our participants did not recognize the attitudes better when they have both tracks than when we had a single track. And so that was kind of interesting. But when you're stuck with this in psychology, when you find a situation like this, you're a little bit, it's a little bit of a problem. Because in fact, there's this question. You don't know, maybe it's possible that the information doesn't exist in the 2 tracks, right? So maybe if I give you 1 track, I give you 2 tracks, you get exactly the same information about, interpreting the situation. Maybe all of the information is in the first track, adding the other one doesn't add any more information. That's one possibility. The other possibility is that this information exists. There is information in the interplay between the 2 tracks, but simply our participants were not able to exploit it, which is also clearly a possibility, right? And when you have this situation in psychology, it's a little bit uncomfortable because you can't prove that there's no information. All you can prove is that your set of participants can't do it. But maybe there's another set of participants somewhere who will be able to do the task. And so in our case, we were lucky here. The first participants were non-musicians, so we went to find a group of expert musician listeners, and we did exactly the same task. And then in these people, you see there's a massive gain of performance when the musicians had both tracks instead of a single track. So it's just the non-musicians weren't able to exploit these cues, but the trained musicians were able to exploit these cues. That was fine. But if we had this group of musicians with exactly the same performance as, no difference between these 2 bars, for instance, we would have been in trouble. We have been, okay, so maybe we don't need musicians, maybe we need saxophonists, maybe we need, redhead saxophonist, maybe we need French redhead saxophonist. You could go fishing forever, basically. And when you look at that type of situation, which is basically getting a proof of is there information in the system, in the stimulus, so that the system can infer this information. This is a task where machine learning excels, actually. And so I'll give you a couple of examples of papers that do this. I've been fishing around for so many months and years for papers who do that kind of proof, because I think it's very, very elegant. And in that paper here, this is a paper by Bart Debout and Patricia Kuhl. These are, it's a different question. This is a paper about motherese. I don't know if you know that phenomenon. Motherese is that specific tone of voice that parents take when they're talking to kids. If I talk to you like this for half an hour, you'll think I'm a bit strange. But when you talk to babies, somehow people do that. The technical term for it is infant-directed speech, IDS. I call it motherese. There's this long-standing question in the developmental psychology. People are interested in how babies learn the world and how they learn to speak and how they learn language and so forth. In this field, they have this question of the possible biological function of motherese. Why would you talk to babies, and is there any cognitive function to doing that? And one of the hypothesis that people have is that in fact when you have this very strange prosody of speaking like this, you are maybe helping babies to learn language. Maybe the way you pronounce the words, maybe you separate them, you mark them with very clear pitch melodies, maybe that help the developing baby brain to parse the different sounds, to recognize what's important in a sentence, what you should learn, what you should drop, and so forth. So this is a question of the sort, is there more information in mother-ears than in typical adult-directed speech for a developing system to learn language? And that's a very difficult question to handle experimentally. It's just you can't really, have adults try to learn mother-ears because they've already learned the classical thing. You can't really take babies because they are learning. So it's very difficult to get to that question. And that paper here makes a very elegant argument. And guess what? They're doing it with GMMs of MFCCs. But what they were doing basically is that they trained, a vanilla speech recognition system on adult-directed speech, and they trained it on IDS, and they're basically looking if the speech recognition is performing better on infant-directed speech than on adult-directed speech. And it's the case that it is. These two graphs here are showing the different probability distributions that are learned by an unsupervised model, GMM, basically on the space of 4 more, so discriminating different phonemes. And to cut a long story short, if you train it on IDS, you can discriminate more different types of phonemes than you do on adult-directed speech. What this paper is showing is that from a computational point of view, the physical information exists in the mother-ears signal that makes learning language easier. I thought that was a really clever argument to make, and it's impossible to make it without machine learning. And this is a more recent paper, again on mother-ears, that was published in Current Biology in 2017. And again, guess what? What they're using is MFCCs and support vector machines. And what they were doing here is kind of a variant of the same thing. They trained a model on discriminating mother-ears versus normal speech. And what they did was training it in English mother-ears, so they recorded English speakers doing mother-ears and separate them from their normal adult-directed English. They trained the model of this, and then they tried to test it on mother-ears and adult-directed speech from other languages, Japanese mother-ears, French mother-ears. And what they found is that the performance didn't degrade at all. Basically, the same model you've learned in English is able to decode, to separate mother-ears in all other languages. And what they were saying, basically, is that there's a universal spectral timbral signature to mother-ears that's, mothers in all language manipulate the statistics of their vocal timbre when they address infants, and they do it in a way that's at least partially universal. So again, this is one of these information exists in this signal for a human brain to compute it, proof by a machine. And that paper here was really striking to me because, again, these are exactly the same tools that I've been using to make my own arguments in that old cognitive science paper that got rejected in 2 days. And this has got published in Current Biology, which is one of the best journals out there. So it's really not a matter of the tools are not the right tools. It's a problem of using them properly. It's the problem of identifying what's a valid scientific result in the field of biology. And we can certainly do it with these tools, but you've got to understand, what is the epistemic value of these results and what makes my old result totally useless. So that's, I've been really happy about finding papers like that. I was actually using that same trick in one of our recent papers. I'll show you quickly about this. We looked at the prosody, so the melody of speech from people who gave answers to like a quiz, like a TV show quiz or something that we set in the lab, and they had to give some answers. So their answers either accurate, true or false, and also we asked them to quantify how much confidence they had in their answer. So you can be right, but you're really not sure you're right. It's like you ask me what's the capital city of Australia, and I'm like, I know it's not Melbourne, Sydney, Canberra. And you can hear from the sound of my voice that I'm really not sure about what I'm saying. I may be true, it's actually Canberra, I think, last time I watched, but my prosody is telling you that you wouldn't bet too much money on what I'm saying. And we were interested in seeing if people could decode the accuracy and the confidence of speakers from their voice. And again, the way we did this was to use a machine learning classifier. And we found that accuracy could be decoded from the prosody even when people were confident. So for instance, if you're confident in your response, a machine learning classifier can still tell whether you're right or wrong. You may be confident and wrong, so you think you're right, but a machine learning classifier listening to the sound of your voice may be able to spot that you're wrong even when you're confident. And we use the same type of argument. There is enough information in the signal for something to decode that information. And of course, like we wrote in the paper, further research should investigate whether actual listeners are actually able to exploit these cues. That's kind of a separate question, but at least we can make this proof of physical information existing in the signal. And these types of proof, they're easy breezy when you submit this to papers. They really fare well with the biological set of mind. We really love these tools, this kind of proof in the cognitive science community. So my first mistake in this was, again, try to build a proof on machine judgment, saying, I have 20-minute songs, I can, get some data from this. The usual response that you get about this is that this may be informative about the properties of the algorithm, but it's not informative about the properties of human cognition, because you don't know if your algorithm is correct, basically. But the real good idea that's hidden in there is to build proof not on the judgments, not on the results of the process, but on the input, on the information that's available for the machine to process. With proofs like physical information exists in this type of signal or behavior, that's enough to simulate the task or to infer certain judgment. So why we are thinking about this, we have input signal, we have some music, we have an algorithm. I understand that I can't really use the results, but we do have a lot of knowledge in the community about the signal processing features to extract from the signal. Even if I don't care about my genre labels, whether they classify correctly or not, I still have a lot of knowledge, and we have even more now with the architectures, about features that are informative, let's say, that are useful to extract from signals for our task. And another intuition that we have is that maybe, these features here, okay, I can get rid of the machine learning classifier, but the input signal processing here is probably quite a useful feature to explain the result of human cognition, right? So we have humans listening to sounds, they produce some judgments, they can tell whether they think the song is happy or sad or whatever, and an intuition coming from MIR is maybe we can be useful in extracting a lot of signal features that we can then use to explain how humans work about doing the same task. And again, that's, I've tried that, and, you don't want to do this. Basically, this was back when I was with Emmanuel Bigon. We just set to do this, and at the time we had the MIR toolbox, which was still very much useful by our friend Olivier Lartillot. And so we had participants come in the lab, they've listened to a bunch of songs, they made some judgments. I think at the time it was emotional valence and arousal, whether they're happy or sad, whether they're positive, negative. And we extracted a lot of features, everything we could extract from these pieces of music, and we basically ran a bunch of correlations between this. And we found things like the emotional valence of music was very well explained by the entropy of the period of the magnitude of the peak of the chromogram. And that's beta coefficient means there's a fairly strong relation. It's a negative relation, but it's fairly strong. And we could also explain the emotional arousal of the music using the standard deviation of the 6 MFCC coefficient, and let me get this right, the average of the third MFCC coefficient, but not the opposite, mind you, not the average of the 6, but the standard deviation of the 6. So when you look at this and you're a computer scientist, this actually works like a joke, right? It's obvious that these things, they explain the data all right. I mean, they correlate, okay, the statistics are fine, but you can't understand anything about this, right? And if you send this to a psychologist, they go like, I don't, okay, your data works out, it correlates, okay, but there is nothing psychological that I can extract, in terms of knowledge from this result. And the reason this is so is that these features that we are using, and this here is the chain of processing of the MFCCs, for instance, when you think of them, you break them down. If a psychologist say, okay, what does this model, where is this in the brain? We don't know. Because these features, they are not designed to model anything in the brain, they're designed to be very good for machine learning classifiers, basically. And in fact, with deep architecture now, we optimize these features with the criteria of classifying correctly, of the outputs. They're not optimized for biological plausibility. So another way to put this is that they have very bad cognitive modularity. One doesn't understand what these features intend to model and what cognitive level we should aim at in the brain to evaluate them. Where could I put a probe in the brain to say, does here this neuronal activity correlate with the MFCCs? Or is it here or here or here? There's no such place you could look at. If you break down the MFCC thing, I don't go into details. Basically, the first few stages are not too bad. Basically, you could say this is kind of a minimalistic model of the cochlea, maybe. This is cochlear in French. basically you have a Mel scale and you go in the frequency domain, and this is basically a bit like a model of the basilar membrane, you could say. Even the log here, you could say that's kind of low-pass filtering on the auditory nerve. The big problem here is the DCT, is the discrete cosine transform, that has nothing to do with biological plausibility. We use this to decorrelate the coefficients because it's very good for learning, to do machine learning afterwards. But this is breaking it completely down, basically. So when you say to a psychologist, we've explained music emotions, it's the third coefficient of MFCC, they say, I'm sorry, but I don't know what to make of this. So again, thinking very long about this, talking to psychologists and neuroscientists about this. And one thing I understand that is actually a better way to use our tools is to try not to correlate the human judgments that humans are able to do down the chain, but to try to use signal processing to explain cognitive features, you could say, to explain intermediary representations that humans may have that they then use to produce their behavior. I'll give you an example of this. In the face cognition, face neuroscience community, there are now very, very powerful models that try to explain musical emotions, not at all by doing, MFCCs of facial pixels, with doing texture coefficients and stuff like that, which works very well for the computer science world, but again have no utility for the psychology. But these features here are higher level features, and what they do is to model basically the activity of individual muscles in the face, what we call facial action units. So you have a feature that models that gesture, another one that models this, another one with the doing this with the nose, with the brow raiser, moving your eyebrows like this. All of these features are like multi-dimensional, they move in time, but when you can explain human judgment based on these features, then it becomes very informative for cognition. For instance, this would allow characterizing, where's my hand, the difference between surprise and happiness. For instance, you have surprise, which is first the eyes and then the mouse, and happiness is the same gesture, but it's first the mouse and then the eyes. And this is the type of work using that type of computer models that get published in current biology. Example from our own work, I'm still talking about this work about social interactions in music. So remember these pairs of musicians that are communicating social attitudes to one another. We looked at this data set a lot, and we tried to identify intermediate cognitive features that these musicians and the listeners may use to decode these attitudes. So instead of trying to decode the attitudes from the raw signal or the MFCCs, we're thinking, is there some cognitive features that we could model with signal processing and that could explain the behavior? And one of them we found was very powerful, was the amount of causality that you have from one musician to the other. Does this musician behavior causes the behavior of the other musician? If he plays loud, the other musician plays loud, plays quiet, there would be strong causality from one to the other. Could be the opposite. Could be, if this one plays loud, then this one reacts. And so you can measure the amount of temporal causality. And you can do signal processing on this. You can do autoregressive models to model this. There's a thing called Granger causality that maybe you know about, which even gives you a statistical measure of how much causality there is from one source to the other. And that was very useful in quantifying patterns of temporal causality in different types of musical interaction. And what we found, for instance, let me get the weather report thing work out, is that, so these are different types of causality. What we found, for instance, is that in the disdainful interactions, there was very, very few interactions where the receiver had any causality on the emitter of the attitude. So if I'm being disdainful to someone, I will pay no causality whatsoever to whatever they're doing. And this is reflected here very clearly. And on the other side, if I'm being caring, that's the opposite. You can't really see the gray level here. And I'm making a fool of myself with the hands again. But basically all the caring information had very strong causality from the receiver to the emitter. If I'm being caring to someone, I will react to whatever they say and not try to have them react to whatever I'm doing. So this causality analysis is, relatively sophisticated in terms of signal processing. We find kind of joy as MIR researchers to do these algorithms and to analyze the music, and they're also very informative for musicians. So the second mistake that I've made, if I want to sum this up, is to try to use signal features that we use in MIR, like MFCCs or what have you, to explain human judgments. Because these features usually have very low explanatory power. One doesn't know what they model, basically. But the good idea that's hidden in these logics is to, instead of explaining the final human judgments with these signal features, is to try to build models of intermediary judgments, percepts, action units, you could say in the face metaphor, which you model with signal all right, but they allow characterizing behaviors in a way that's modular, that's measurable, that's verifiable, that's very useful for cognitive science. Now, even when you do this, you're not really out of the woods yet. Because one thing that we do very often is that we have features, we have some target behavior, and we'll just basically, in all of the behavior that's here, you find these features. Basically, we do a lot of correlation, we do a lot of analysis in quantifying how much of this there is in this. That's the typical methodology we have in MIR. When we do this in cognitive science, it doesn't work very well. So in the case of the causality example that I just gave you here, what we found from this histogram of things was very clear. Again, the carrying interactions, they had a lot of decoder to encoder causality. So the one who was being carrying let the other influence their behavior. In the domineering interaction, it was in the other way around. If you look at the bar graphs here, the encoder had a lot of causality on the decoder and did not listen to what the decoder was saying. And the disdainful interaction, we had no causality from decoder to encoder. And when you have bar graphs like this, like the distributions of different types of causality in the different interactions, you don't even need to run stats. I mean, it's very clear that these interaction situations are very discriminated by the different types of causality. So we were very happy about this, and again we sent this to a journal called Cognition, and again this came back in a bit more than 24 hours, but not much more, with this argument that these are extracts from the anonymous reviewers. While this is a neat little study with sophisticated acoustical analysis, blah blah blah, the mechanisms behind the observed effects are not elucidated in psychological terms. So that was a bit frustrating to read and a bit complicated to understand. And it took me again some weeks and months to really understand what's behind this. And it's in fact a very simple idea, but it's like a secret weapon. Nobody will tell you this. A variant of that same argument is to say this study provides no mechanistic insights. And when you have this and you have these words, mechanisms, mechanistic, what the psychology, cognitive science word is trying to tell you, in fact, is that you're doing a proof which is based on correlation, and correlation doesn't imply causality. This is like science 101. It's very, very simple. You just would wish that reviewers would say, you're doing correlation and not causality. No, they're saying, the observed effects are not elucidated in psychological terms. Okay. But when you understand that, there's plenty of writing in the biological world, and in fact, biologists even fall for this. So this is a very, very useful paper. It's actually by a couple of immunologists, in the medical science, and it's a paper called Descriptive Science, where two journal editors explain why they reject paper, in fact. And in their world, they reject a lot of paper for being descriptive science, and they want to explain what they mean by this. And they give this example here. I should let you read this maybe, but basically they're saying, imagine you have some gene that is, increasing some reaction, and we think it's important in this because you see the expression of the gene that changes during the infection. So you think maybe that protein is useful, is important for that process of inflammation. And they say such an inference cannot be made on correlation alone, because correlation does not simply imply a causal relationship. This study might be labeled descriptive and assigned low priority. On the other hand, imagine the same study in which the investigators used the initial data to perform another experiment that established that blocking that protein has a certain effect, while increasing the expression of blah blah has the opposite effect. So basically, by manipulating the system, the research transforms the study from being simply descriptive to being what they call here hypothesis-driven. Hence, the problem, they say, is not that the study is descriptive per se, but rather that there is a preference for studies that provide mechanistic insights. So what this is saying is that if you observe a correlation, what you should do next is to take your system to manipulate one variable and to see if the other variable is moving in the right direction, in the predicted direction, right? You're saying that this goes up, then you need to go back at your system to create another experiment where you manage to manipulate this and check that this relation is preserved, that you basically have a causal effect between the input and the output. And that's like a secret weapon. If you understand this, it's relatively easy to do in most of the cases, and it will really, suddenly you start to think like a biologist. And this, bias towards studies that provide mechanistic insight is even a joke in psychology. I have people on Twitter, it's like a meme, basically. You have things like red squirrels drive so slowly, and you say, why is that so? But what's the mechanism? It's observing something isn't sufficient. The reviewer would say, okay, but what's the mechanism? Can you move something to see if the other thing moves in the right direction? So instead of correlating and using analytic data, what we should do is to build generative models that are able to model the data. So instead of, say, trying to correlate signal things to the output, what we should do is to put the algorithm here, in fact, that has sound in the input, sound in the output, a transformation model that goes from one, and then basically you could take a sound, have humans judge it, they produce some output, then you modify something in the sound and you see if the human judgment moves in the right direction. So we got back at this cognition reviewers, they're saying your study has no psychological relevance at all. What they were meaning, in fact, is that we observed that all of the, affiliatory interactions at that type of causality and all of the domineering interactions at the other side of causality, they're saying this is merely descriptive, there's no mechanism there, not interesting. What they were asking us to do, in fact, was to do the manipulative version of this experiment, where we would take a piece of music, inverse the correlation in it, the causality in it, inverse the temporal causality in it, and see if that inverse the human judgments that people do on this. If we have this, then we can prove that the humans actually use that feature of causality to make their judgment. And when we realized this, 95% of the job was done, because this was very easy. We had separate tracks. It was as hard as opening Audacity and add basically 1 second of delay in one track. This was ahead of time before, this is now behind time. We just saved the track again, we played to humans, and we showed that the results were totally reversed. So tracks which were, judged as being caring, you just desynchronize them as this, and they're judged as less caring and what have you. We did this in half a day, basically, and sent the paper back at the reviewers, and I should have copied the cover letter or the response, letter from the reviewers, but they basically loved it. And it was the same exact data. It was just, half a day of extra work, showing you how important it is to actually understand what is considered a result. If you can have 20 pages of fantastic correlations, and we made everything. We recorded novel behaviors, we recorded the musicians, we've found the features. We were finding this idea of temporal causality. We found a model, an algorithm that can extract these features. We found that it correlated perfectly well with the human judgments. Didn't compile. And you had 1/2 day of work showing that if you manipulate those features, it changes the human judgment. Suddenly you're in cognition. So that was really one of these epiphany type of moments for me, trying to really understand what's at the core of what makes biology different from music information retrieval. So we've made this over and over again. Once you get the secret weapon, you see opportunities for doing this all the time. So one thing we did, for instance, was looking at a musical question. There was this question in the music cognition world of whether music conveys emotion by imitating vocal expressivity. So for instance, when you have very bright violin sound and you find this positive and happy, does this sound happy to you because in fact the bright violin timbre sounds a little bit like it's smiling compared to a more dull or dark timbre? I mean, when you think of this, you could do hours of correlations between the timbral features of the violin and the emotional reactions. We know exactly what's going to happen with this in the reviews. But if you spend a little time building an algorithm that can transform the spectral shape of your data in a way that sounds a bit more smiling, and we can model this, and it's a decent MIR task, but we can do that. Then you have a ready-made experiment. You take a piece of music, you increase the smiliness in it, you check that it is perceived as more positive than if you decrease the smiliness of the same piece of music by the same participants. Works exactly the same. I mean, it works exactly as predicted, and these are valid results in the cognitive science world. So that's really kind of a design pattern of using our tools to produce results that are interesting for the biological community. So again, if I sum this up, my third mistake was to say we can correlate a lot of stuff together, but when we do this, it's usually rejected as being non-psychological. And the key word here, the secret weapon is this word mechanism. When you have the question of yes, but what's the mechanism? What you need to understand is that people is asking you for causality and not correlation. And to prove causality in this culture of biological science, you need to manipulate the system under study, and you can typically do this by manipulating the stimulus. You have one stimulus, you can turn it one way or turn it another, like switch on that feature, switch it off, and see if the human behavior is predicted in the same direction. So it's really important, in fact, and I found this very, very fruitful in the past few years, to use the tools of music information retrieval, signal processing, sound synthesis, to build generative models, computational models that can generate and transform the acoustic properties of stimuli, of voice and music, so that we can demonstrate causally that the impact of these features that we manipulate have an impact on behavior and cognition. It took me 15 years to get to this, basically. I'm happy to share that tip to you if you're interested. And the current agenda of my research group, by the way, is really based on this idea. We have oops, where am I? We have a website here. This is about time. I want to keep a few minutes for questions and interactions with you. I'm so sorry I can't be here, in presence. By the way, I'm doing this virtually, but I hope we can have good discussions. Few final personal reflections of all the journey. So it's been a heck of a journey. Basically it took me at least 10 years to be able to publish valid cognitive science research in journals in this community. Interdisciplinarity, I've learned, is a very long learning process. And in my first few slides, I was talking about mastering the language and then mastering the culture. I remember when I first came to Japan. Japan sounds daunting because Japanese is so complicated and so forth. Actually, mastering or at least having a decent level in Japanese language is doable in a few months. The problem is then you speak very well Japanese, but you speak like a Westerner. And after 5 years in Japan, I had still no idea on how to produce a sentence that sounds realistically Japanese. The words were okay, my grammar was okay, but I could never invoke the type of thought process that would generate genuine Japanese sentences. And in my interdisciplinary journey between computer science and biology is all the same. Take a few years to get the neuroanatomy terms and to be able to run the EEG machine and to do the stats. But once you're done with this, it takes a lot more time to then understand what is a valid result for these folks there. And to understand what is considered interesting for biology. And this, for instance, mechanistic insight thing took a lot of years to figure out. And this is hidden lore, basically. Nobody teaches you this. It's also a long journey. You'll excuse the snobbery a little bit. I can have this snobbery because this citation count is actually not very impressive. But basically, these are my PhDs for a few years. You publish on the MIR and you go, what, like this? And then you change field and you have to be prepared for a rough ride. This is past 2022. If you look at this, I basically have the same citation count this year than I had in the final year of my PhD. So it's a long journey. You have to be prepared to have fun and to love learning, and I would really recommend it. One thing, it's a little bit cliche, but I think this talk hopefully conveys it pretty well. You have to cherish the rejections. They're the only way you'll learn something valuable and new. I had these, journals not wrote back to me and said, this is not mechanistic, this is not relevant for psychology, this is not, you're judging the algorithms and not the humans. I've had, the same frustration everybody has with a rejection. But without this feedback, there's no way I would have the understanding I have of this new discipline I have today. Which means that you should even seek rejections. And that sounds crazy, but, it's very important that if you're interested in moving to another field or to applying your current skills to another set of questions, you have to confront the people who do that research. You have to send the damn results to cognition. And yes, they will break it down in 24 hours. And yes, this is going to last 10 years. But that's the only way you'll get the feedback. And, you have to be prepared to be stupid, to write things that you think are great today and you'll look back 10 years later and say, but no one else will. You will not find this knowledge elsewhere. You will need to do it yourself. And another point that I have from this is when you go from one field to another, it's actually very easy to look down on the other community. At the beginning I was like, but these psychologists, they're really silly. I have all of these algorithms, they ignore everything about it, they don't understand. And you go to them saying, I have the silver bullet for all of your problems, and guess what? You don't. And I know that I'm in psychology, I will sometimes look down at computer scientists saying they have no understanding whatsoever about biology. It's very easy to brag a little bit about this. You have to remember that research is a social activity, that different research communities, biology, computer science, they have different cultures, and you have to be kind and nurture empathy and understand why the psychologists would reject this work. They have very good cultural reasons to reject. They're probably right about rejecting it. It's very difficult to understand it, but just the fact that you don't understand why they reject means that they're wrong. They're not. And likewise, probably computer science has a lot of insights to offer to neuroscience, but it's mainly being ignored by people who simply don't understand our code for doing research. So it's very, interdisciplinary research is an exercise in empathy, and it's very important. And talking about empathy, I have to cycle back at the idea that here I am, I've been away from this community for 10, 15 years. totally absent from the scene. I haven't followed results at all. And here I am invited to give a keynote at MIR in 2022. So I must be really grateful about this. And thank you very much for having me back. And I hope we can have some time for questions now. Thank you very much.